All right, I think we're going to go ahead and get this session started. So welcome to this session on crypto topics, selected topics. I'm the moderator, Seth Nielson. Briefly introduce our speakers today. Our first speaker today is Dr. Sandra Guasch, and she is a staff privacy engineer at SandboxAQ, where she's worked on post-quantum resistant privacy-preserving technologies and has worked in areas of applied cryptography and cybersecurity, including the design and evaluation of electronic voting, secure software lifecycle management, secure system design, compliance, and ethical hacking. And she'll be speaking today. Her talk is The Hitchhiker's Guide to FHE.
Thanks for the introduction. So yeah, thanks for coming to my talk. This is going to be an introduction to FHE. And I guess you may have seen other introductory talks to the topic, so I try to add some contents that you may not find in these presentations. I try to be a bit original. And first of all, I wanted to talk about why we think that fully homomorphic encryption is something that is actually really important to care about and to talk about. Well, some people say that FHE is like the holy grail of cryptography, since we can perform any kind of computation over encrypted data. And as you can imagine, this at the end, it's a very important building block that enables very interesting functionalities, mostly related with data privacy, which is something that is of critical importance, I guess always, but also now it's becoming like more and more important also with the surge of AI and other related systems. And when I talk about performing arbitrary computations over encrypted data, I wanted to be very specific. So basically, what FHE allows us is to compute to operate ciphertext in such a way that we can obtain as a result either the addition of the underlying plaintext or the multiplication of those plaintexts. Okay? And from this, the idea is that we can build any kind of program using FHE. So what I will cover in this talk are the following topics. First, I will talk a bit about how do FHE schemes work. Then I'll talk about some of the use cases where FHE is actually pretty interesting, and also talk about some of the considerations or things to take into account when we use FHE. I won't cover the topic of answering to the ultimate question of life, the universe, and everything, because luckily this has already been solved. So yeah, let's go for how do FHE schemes work. And well, you may have heard that FHE has a lot to do with noise, no? At the end, noise or the encryption, noise in encryption is what conditions like the limitations that we have in FHE, the inefficiencies that we have in FHE. So it's kind of like a very important topic. And I wanted to illustrate what this noise is about and where it comes into play. And in order to do that, well, we should consider that modern FHE schemes are mainly based on lattices, and most of them are based on the learning with errors problem. And I didn't want to get a lot into mathematical details. In fact, I'm not a mathematician, but I wanted to just give like the notion of it. So basically, what the learning with errors problem tells us is that imagine that we have vector S, the secret vector S of integers and integers modulo sum q, for example. And then we multiply it by a known matrix A of integers also modulo q, and we add to it a noise vector of values grabbed from some error distribution, okay? So what the learning with errors problem tells us is that even if we know the result of this computation, we cannot trace it back, or we cannot get back this secret vector S, okay? And the way we use this for encryption basically is this one. So we can encrypt a message by using this learning with errors problem as a basis. And the idea is that the first part of the ciphertext will be the matrix, the known matrix A, and the second part of the encryption is the result vector B plus the message that we want to encrypt. Okay. In order to decrypt, the decryptor can multiply the secret value S by the known matrix A and subtract the result to the second part of the encryption. And as a result, we get the error plus the message. And if we have selected our parameters well, we are going to be able to round this in order to get the message. No? We are going to get rid of the error. And I wanted to put some values here to take into consideration like which are the dimensions or what we are talking about. No? And this is like the second part of the ciphertext, so we can see it's S by A plus E plus M, and E plus M is what we are going to recover after decryption, right? So according to some security levels, for example, we could have a secret vector S of length 800 bits, and then each one of the components of the array of the matrix A could be 32 bits. And then we have this error array and this M array, no, that both have to add up to an array of 32 bits too. And we have to, for example, for a given level of security, we could have an error level of, let's say, 20 bits. And, well, we cannot arbitrarily choose this value, no, because it has to correspond to a given security level. But we also have to take into account that we need to leave some extra bits for this error to grow while we perform homomorphic operations. And then we will be left out with some other bits where we can actually put our message. And here, for example, it could be like 4 bits. So we can see that we need actually a large amount of information in order to be able to encrypt a 4-bit message, okay? So this error that I am talking here about is the noise in LWA encryption, is the noise in FHE, sorry, that is going to be increasing every time we perform an homomorphic operation, and we need to make sure that this error doesn't overflow, no? And it doesn't it doesn't use some of the bits that we are using to represent the message, because otherwise, once we decrypt, we are not going to be able to recover the value that we expected. We are not going to be able to recover the message. And yeah, the way the noise or the error grows, it depends on the type of operations that we are performing, the type of homomorphic operations, no? When we add two encrypted messages in order to get the addition of the plaintext, the error is also, the equivalent error is added. In case we do a scalar by ciphertext multiplication, the resulting error is equivalent to this scalar by the original error. And when we compute the product of two ciphertexts, actually the resulting error is a function of one of the messages and the two previous error levels. And usually it's more or less like doubling the error, which means that actually the noise is increased, like the operation that increases most the noise is usually like the product. And this is why also when talking about FHE schemes, sometimes you will see that we talk about them or about the different parameters that we choose according to the multiplicative depth of the circuit that we want to compute, no? Because it's the amount of multiplications that the ones that that lets the noise increase the most, no? And it's going to be the one that actually limits how many computations we can perform. So the idea is that with this error growth, with this noise growth, we have a limit on the amount of computations that we can perform. And this is a limitation of what we call the somewhat homomorphic encryption schemes, no? Schemes where we can compute different types of homomorphic operations, but we had this limit on the bits that we can use to represent the error or noise. Then in 2009, Gentry introduced the concept of bootstrapping, and this bootstrapping operation allows us to reset the noise level. So effectively what it does is that it enables constructing a fully homomorphic encryption scheme from a somewhat homomorphic encryption scheme, because we had a scheme where we could perform homomorphic computations up to a certain level where we were using all the bits available for the error or for the noise, and then we can reset thanks to the bootstrapping and continue computing. So we don't have this limitation. And the way it works is the following. That's a simplified representation, but basically the idea would be, imagine that you have two encrypted messages, M1 and M2, each one with some bits that are used for the message and some bits that are used for the error. And then as you compute different operations with these messages and other encrypted messages, the error level is going to be growing until you reach the limit, no, where you are using all the bits. And then at this point, you can perform this bootstrapping operation by actually doing a key switching operation. So what you do is you encrypt again that message that was the encryption of the function over the messages with a new key. Then you decrypt using the previous private key, and through this decryption operation, you remove the noise that was accumulated before with the previous operations, no? And as a result, you obtain the encryption of the function that you had been computing over the messages. Sorry, I was trying to count for the time, and then I didn't press start. So basically, by doing this, you remove all the noise that you had accumulated from the previous computations, and you only have in blue the noise created by doing this encryption with the new key and the decryption operation. So actually, the noise level has lowered, right? And well, this is what I was explaining about the noise levels and the bootstrapping operations. Like these are like the basic notions, and of course, there are many different FHE schemes, no, with different properties, and I wanted to illustrate it here. That, for example, starting with the first notion of homomorphic encryption in 1978, we had then somewhat homomorphic encryption schemes until Gentry's publication about bootstrapping, and then we had and this is only like the most relevant schemes, no? But we have different, a lot of schemes with different properties, and the latest ones that were published were, for example, TFHE and CKKS, no? And well, they all rely on different assumptions, but basically the reduction, like all the assumptions at the end, rely on LWE. But I also wanted to show like the different schemes that we have in FHE in another way that is more based on like the philosophies that they follow, no, the strategies. For example, we can see somewhat homomorphic encryption as the baby form that then evolved into FHE through the bootstrapping operation. And then from there, we can see that there are like different schemes that can be split into these two different strategies, no? One strategy is leveled FHE, and this is the strategy followed by different cryptosystems like BGB, BFB, or CKKS. And the idea is that we decide at the beginning, when defining like the parameters of the scheme, the size of the parameters that we are going to choose, which is the maximum multiplicative depth, or which is like how many operations, homomorphic operations, do we want to perform with our, with our encryption scheme. So we predefine all these levels, all these different levels of multiplicative depth that we will have, and this will condition like the size of the parameters of the encryption scheme. And the idea is that in those schemes, bootstrapping is usually quite expensive, so we want to try to avoid that. Then there are different, there are alternatives like parallelization, no? or packing different messages, several messages in the same ciphertext so that we can actually optimize these operations. But the idea at the beginning is, okay, we want to try to do as much as we can without doing the bootstrapping operation. And then we have the other strategy that is the other way around. Actually, we want to have a fast bootstrapping operation so that we can actually even bootstrap after each computation, and we don't care about which is the maximum multiplicative depth of our circuit. We don't have this limitation. And then there are approaches, newer approaches like Chimera or Pegasus, new proposals, no, that what they propose are not new schemes, but actually ways to switch between schemes, because the different schemes serve different use cases. They go like yeah, some scheme may be more optimal, not maybe present a optimal setup for a given use case, but then maybe you are at some point in your program where actually would be super nice if you could jump to the other scheme. So this is what the proposals, these proposals are trying to achieve. And yeah, just to illustrate a bit also like how these different schemes serve different use cases, I added here a comparison table, no? Well, I didn't intend to be super exhaustive on the properties, but just to give an idea, no? For example, schemes like BGB or BFB are good for working in infinite fields or for computing polynomial functions. And TFHE is more related to Boolean arithmetic, but it also, because it has this functionality called programmable bootstrapping, it goes very well with also pre-computed random functions, like, for example, an SBox. And CKKS is more, it's intended to work on approximate arithmetic. So we can see, no, that we have different schemes that actually work well with the different representations of messages and information that we want to use, no? And also, as I showed before, no, they follow different strategies, like maybe slower bootstrapping operation, but then some schemes allow for parallelization, while some others don't. So we have like these different trade-offs, and this is why also like having this scheme switching techniques is very helpful to be able to jump and see in which case we can, which trade-off is better for us, no? So yeah, now that we have talked a bit about how FHE works and which are the main, like talk about some of the schemes in a very high level, I also wanted to talk a bit about the use cases. The first one that is very close to me because I used to work on electronic voting, and I don't know if there's somebody from the CR, but I think for voting, no, you use also an electronic voting protocol called Helios. So, for example, in electronic voting or in blind auctions, you can use FHE in order to compute the result, for example, of an electronic election without having to decrypt the individual votes from the voters, which means that we don't need to break their privacy, no? And it's a very efficient thing to do. And for example, in the case of electronic voting, we could even do with partial homomorphic encryption. We don't need even to compute multiplications in some of the cases. Then also, yeah, there is another use case that is dark pool trading that I found interesting. Dark pool trading is used by mainly by financial institutions in order to perform large operations, and in order to not to influence the market, these operations are sent in an encrypted form. So you have a pool of buying and selling orders, and there is only the values are only decrypted when there is a match, and not after and not before that. So we use the homomorphic properties in order to find this match without decrypting first. And then, of course, another very interesting use case is privacy-preserving machine learning. No, imagine that we have a machine learning model in a SaaS service, no, where we can kind of provide this diagnosis information based on patient data, but of course, we may be reluctant not to send our medical data to a cloud service. So with FHE, we can actually send the data encrypted and still retrieve the diagnosis information without leaking the medical information to the server. And then in a similar way, we can use FHE in the training phase of these machine learning systems, no? And we can train using private data sets, so that the machine learning model or the centralized server that is training this model doesn't learn about that, or we can even enable collaborative training, like, for example, federated learning, no? Where we have different tenants with different data sets, and they together train a model without actually leaking the information of the training data to the others. This can be very interesting, for example, also in medical studies where each hospital may not have a lot of different cases for a given disease, for example, and this is very practical for rare diseases, where actually being able to collect the information from a lot of different entities can be really useful. But at the same time, you have a very strong regulation saying, okay, be careful how you protect, no, how you share your data. And well, there are many more use cases, no? Being able to perform private searches, being able to delegate a computation to the cloud. Private advertising is something that I find also very interesting because for attribution, for knowing how an advertising campaign worked, usually like browsers and third-party entities track a lot of information from us, and actually it's something that could be done really efficiently with FHE. Checking if my password is part of a database of leaked passwords, or enabling private smart contracts, for example. And then some considerations about using FHE. I don't know how I'm, 10 minutes? Okay, I think. Okay. So some practical considerations about using FHE. Well, the basic operations that we have are the ones from very similar to any encryption scheme, no? We have a key generation phase where it depends on the type of scheme, no? But usually we will have a private key, a public key, a private key, and then we have an evaluation key, which is more specific to FHE. Then we can encrypt messages, we can perform this evaluation, no? So that we can get, as a result, the encryption of the evaluation of the underlying information, and we can decrypt. And like, in a very simplified use case of like a delegated computation, we have here my cat that is the user that wants to send some messages for some computation to be performed in the cloud, that in this case is represented as the preferred carton paper box. And in this case, the user will use the public key of the encryption scheme to encrypt the messages, as usual, and then send this ciphertext, the evaluation key, and the description of the function to compute to this remote server. So then the server will compute the function over the messages. Here it's an addition, and then send back the result. That's like a super simplified scheme, of course, but yeah, there are many others that can be applied. Yeah. Just wanted to illustrate that. And we have been talking about, like, I said at the beginning, no, that FHE enables to compute the encryption of the addition of the messages or the multiplication of the messages, and I said super happily, yes, so you can represent with this any program that you can imagine, and everything is going to be fine. But actually, it's quite difficult, no, to try to represent an arbitrary program as a set of additions and multiplications, and also then, if you do that naively, it may result in a program that is actually really, really inefficient. So you have to also take care of optimizing at the circuit design level, but also then at the encryption scheme level. So what we would like is ideally, to have this super nice translator that, so I say, okay, this is my program, then can you run it like, I want to run it in FHE, and that's it. And then it puts the program using FHE. Also, if possible, that it can run optimized for a specific hardware, because we care a lot about all the potential optimizations that we can perform, as FHE systems are usually quite slow. So that's what we would like to have ideally, And it is not trivial, and well, when thinking about all the considerations, all the things to take into account when working with FHE, something that came into my mind is the concept of encaje de bolillos. I don't know if you can see it in the picture, but it's a very delicate lace working technique that not a lot of people know how to do, and it feels quite a bit like designing FHE systems. Now you have the FHE practitioners that are experts in this field, and it's very difficult for somebody that is not an expert to start using FHE, okay? And this is why, this is mostly because we need to take into account many things. Now, as I mentioned before, how do we translate an arbitrary program into a circuit of multiplications and additions that is efficient? Also, we cannot have branching in the program, or we need to always consider the worst case scenario, because otherwise we would be leaking information. Also, we can optimize for batching different messages in a given ciphertext, and also parallelization. We need to choose which is the scheme, because we have seen that there are many schemes that serve different use cases. And which parameters do we select from that scheme? We need to know how do we represent the plaintext. We need to be able to handle very large ciphertext also take into account how the noise is growing to see where we need to perform the bootstrapping operation and so on. Then we have optimizations at the arithmetic level and at the hardware level, no? So a lot of things to take into account. And this is why we have a lot of tooling that helps with that. And what I see is that the tooling goes from like the more generic entry-level thing to the arithmetic libraries, for example, that is like where you require more expertise in order to be able to use this in an effective way, no? And for example, we can have frameworks or pre-generated circuits for well-known functions, like training a neural network or some specific protocols. Then we have the compilers or transpilers that usually take as an entry level a circuit and tries, depending on the compiler, they may cover different phases, no? But usually they will provide already the code optimized for a given hardware, if we can. Then we have the FHE libraries that usually are specific for each scheme. And then we have the arithmetic libraries that power, no, the underlying functions of the FHE schemes, like polynomial operations, FTT and NTT, and we can, of course, also have optimizations in that area. So, yeah, a lot of things to consider. I also wanted to briefly talk about the security. So basically, in FHE, we don't have integrity by default. No, FHE is more like about the confidentiality. So we need to take into account that before decrypting, we may want to verify that the function that was computed over the data is actually the one that we expected. No? And so usually FHE is combined with zero-knowledge proofs. Also, there is no circuit privacy by default. It cares about the data, not about the program itself. So there may be, like, if we also want to keep that secret, we may need to apply other techniques. Also, because the FHE schemes rely on the learning with error problem and usually use lattices, no? They are quantum-resistant schemes. And then something to take into account also is that they provide IND-CP security, so basically you cannot allow an adversary to get a decryption of any message. You need to have some control of like which was the operation performed over the given message, or whether it comes from a trusted party, because otherwise this could be used to, at the end, leak information about the private key. And yeah, then I guess the elephant in the room, well, basically the question would be, no, if FHE is practical yet, and well, right now, the latest numbers that I know is that we still have a slowdown of 5 to 6 factors of magnitude, depending on the functionality that we want to implement. But there are a lot of efforts in progress that I think they are very interesting. One is like more about the democratization of FHE, no? Being able to, like, facilitating that everybody can use FHE, no? All the developers can use FHE in their programs. And for this, there is a lot of work going on in the compiler side and in the framework so that it is easy to use. Then also I talk about this scheme switching functionality, which can be used to be the most efficient possible depending on the use case or on the part of the circuit where we are. Then also there are other initiatives about bringing some interesting features like programmable bootstrapping to the most modern FHE schemes. And then of course there is a lot of work on hardware acceleration, like for example the DeepRive initiative, so that we can reduce this slowdown, no, and be able to actually handle all the data in a private way, and that it doesn't come, it doesn't result in a very high cost, no, so that it can be used widely. And yeah, I think that was it. I used a lot of references that I found very interesting for the talk. So like list of libraries, compilers, and things like that. So, well, you won't be able to see it here, but I guess they will share the slides at some point, and otherwise I will be happy to share them with you. You want to take a look. And yeah, that was it. Thank you.
All right, let's thank our speaker. Design reviews on topics including embedded systems, post-quantum cryptography, and blockchain ecosystems, as well as many others. Today, he'll be talking to us about cryptography, common vulnerabilities in modern programming languages.
Yeah, thank you, Seth, for the introduction, and thank you everyone for attending my talk today. So as described, I will be talking about unsafe cryptography or common vulnerabilities in modern programming languages. And my name is Paul, and I work at NCC Group, which is a global cybersecurity consulting company. But specifically, I work in the cryptography services practice, where we review and we audit cryptographic implementations. And so, I mean, not only implementations, sometimes customers come to us with cryptographic designs, and we kind of have to try and find vulnerabilities in the designs. But more often than not, we look at implementations. So that could be implementations of primitives, maybe like in embedded systems. It could be implementations of protocols like TLS. Sometimes we look at blockchain nodes or even smart contracts, or even more advanced schemes like fully homomorphic encryption that we have just heard about. And so in this slide, I was just kind of trying to categorize the type of vulnerabilities that we typically find in about 6 kind of high-level buckets here. And one very common area for issues is around randomness. And so randomness is a pretty hot topic here as well. And so that's a place where we usually look for pretty quickly, and we still do find issues around randomness pretty often. For example, around sampling of random numbers, maybe some modular biases are introduced when trying to generate random numbers. Sometimes also the incorrect seeding of pseudo-random number generators or the use of non-cryptographically secure PRNGs. Then we have a category for algorithm confusion. So this would be, for example, when sometimes developers use a hash function to try and encrypt data. So kind of like misunderstanding the intrinsic security properties that the algorithms are providing, or maybe thinking that encrypting data provides integrity if you're using like a very simple block cipher mode of operation. Another common area is around key management. So key management could be things like a leftover firmware signing key that has been left in a device, or maybe some key rotation that is not being handled properly. And then we have crypto primitives and protocols, so that's maybe kind of a catch-all category where we find issues around low-level arithmetic, for example, in elliptic curve cryptography, something that we find pretty often as well. Side channel attacks is also a big topic for us, particularly non-constant time code. So you may know that if you use non-constant time code to deal with secret data, you might leak some information about that secret data based on the timing that the execution will take. And finally, the last item here is around programming. So this could be kind of like dumb programming mistakes that people have made in their cryptographic implementations. And the focus of today's talk is going to be about this last category here, where we'll talk about some common vulnerabilities in implementations of cryptography. And one thing that I will not talk about today, but I wanted to highlight before jumping into the more specific examples, is that we tend to see more and more issues related to AI-generated code. So sometimes we find really, really dumb mistakes that were just spat out by let's say, ChatGPT, and people simply copy-paste the code into their implementation without really testing it. And so I'm not going to expand more on that today, but I would just advise you in being careful with those AI tools. And maybe to explain my title here, because I don't want to antagonize anyone when I talk about modern programming languages, but what I really want to highlight is that I want to talk about languages that are memory safe, so languages where buffer overflow issues should not happen. Also, those languages tend to have pretty extensive standard libraries, and so you might already have access to all the crypto primitives that you need. There was an interesting report by the White House published in February of this year, so a few months ago, which explicitly called out for memory-safe languages to replace C and C++. There's a link to the report in the slides. And in that report, the programming language Rust was explicitly called out as being a very viable option to replace C and C++. On the right-hand side of the slide here, I found this interesting chart in an IEEE post from a couple of weeks ago, dated August 22nd, which highlights the top programming languages of 2024. So this was kind of like a very, very general study about what programming languages were in use. And it's specifically, like the subtitle of that article is how TypeScript and Rust are among the rising stars of programming languages. You might not really be able to see it, but Rust is still kind of low here. TypeScript is a little bit above it. We see that Python, Java, C, C++, so the usual suspects are still very, very much in use. But I think if we look at the implementations that we look at, the picture is very different. And so I added a bunch of adjectives under that chart here. So this is a very contextual and personal type of chart. I didn't count every single line of code of the projects that we review, but I just wanted to give you an idea of the type of languages that we see. And so Rust is a clear winner here. The majority, or maybe a majority, of the projects that we review are currently written in Rust. So when people nowadays want to develop, want to write like modern cryptography, for example, when they implement fully homomorphic encryption schemes, Rust is a very clear choice in this case. Go is also a second, kind of like a close second one as well. And then we also tend to review languages like C++ and C, which are still pretty prevalent nowadays, especially for embedded systems, even though Rust is coming pretty close to being able to achieve that as well. Here's an interesting case study. In case you might not be convinced that Rust is the way to go. I mean, it might not be the way to go for every application, but there was an interesting blog post by the Google security team, which kind of compared the number of vulnerabilities in recent Android versions. And that blog post highlights that Rust is supported since Android 12, so that would be since 2021. And since the introduction of Rust, there has been a pretty significant drop in memory safety vulnerabilities. I think they list about 223 vulnerabilities reported in 2019, and then that decreased to 85 in 2022. I pulled out two quotes from this article, and I guess I can just kind of read them verbatim here. But essentially, Android 13, which was from 2022, was the first Android release where a majority of the new code added is in a memory-safe language. And then, maybe coincidentally, but I don't think so, 2022 is also the first year where memory safety vulnerabilities do not represent a majority of Android's vulnerabilities. So more memory-safe code means less vulnerabilities with respect to memory, which kind of makes sense. The article draws a correlation. It doesn't say that there's a clear causation because there's still a lot of legacy code, but still an interesting case study. And I hope that with that I have kind of convinced you that memory-safe languages are the way to go. And so this talk will use Rust as an illustration to highlight some of the issues that can come when developing using those modern programming languages. Some parallels can be drawn to other languages, so I'm going to have about 5 very specific examples. Some of them only apply to Rust, but some of them are also applicable to other languages as well. And so I'm also hoping that this talk will be an introduction to Rust for the people who have not seen it before. And for the people who have seen it before, maybe it will be a good reminder of the type of programming practices that should be followed. When developing Rust code, there is a very interesting and important website. It is this Secure Rust Guidelines that I have linked here as well. And so that website lists a few things that should be performed to develop secure Rust. And so it talks about things like those tools, cargo outdated and cargo audit, which are very, very important tools in the Rust ecosystem to kind of deal with the dependencies. And so when you build a Rust project, you may have a number of dependencies. And then, for example, running cargo outdated will allow you to, or it will highlight all the dependencies that are out of date. And will highlight like how many versions it is out of date and things like that. And similarly, cargo audit will look at all those dependencies and will check whether there has been a CVE reported for one of those dependencies and explicitly highlight it if it could be present in the code base. That resource here also talks about integer overflows, panics, unsafe code. So unsafe, kind of like a throwback to the title of my talk, but it's a keyword that can be used to perform unsafe operations. So obviously there's some guidelines around that. It should not be used for things that can actually be too dangerous, and so on. So lots of interesting guidelines in here. Unfortunately, there's nothing about specific bugs in the resource. And maybe for good reason, maybe we shouldn't list specific bugs in a more generic resource like that. But I'm hoping that this talk would kind of present some interesting specific bugs in Rust and other languages. And so the first topic that I want to talk about today is the generation of random vectors. And as we have discussed before, Rust is a memory-safe language, so when you create an array, for example, you don't necessarily instantiate an array of a given size using malloc, and then you populate it with whatever. With Rust, you have access to vectors. Vectors are a contiguous, growable type of array, and so you would instantiate a vector using this new function, in this case here, and then you can push elements to the vector using the push function here. And so, for example, we instantiate vec, and then you push 1, you push 2. And if we were to print out the content of the vector here, we would have what I have put under a comment on the right-hand side here, which is a vector containing the elements 1 and 2. If you already know all the elements that you want to populate your vector with ahead of time, you might not want to push elements one at a time. So Rust also provides a very helpful macro, this vec macro. And so a macro in Rust is essentially some sort of keyword followed by an exclamation mark. And so the vec macro is provided for convenient initialization. And so in this case, you would do vec exclamation mark, and then the content of your array, and then that would instantiate a vector with the elements 1, 2, 3. There's also a nice shortcut. A vector can be initialized with each element with a given value, which can be more efficient in specific cases, and you would do that by specifying the value that you want to initialize your vector with and the number of times that it should be repeated. And so, for example, doing a vec of 0, 5 will instantiate a vector of 5 0 elements. So now, what happens if you try and generate a vector of random elements? And so the code snippet here essentially instantiates a random number generator, and then it uses that last macro syntax to try and generate a vector of 8 random elements by calling rng.gen and then repeating that 8 times. And so here, I'm going to print the value of the vector. I'm just going to have a sip of water and let you think about what could be the output of that function call. So you may have guessed it, but if we print out the content of the vector here, the same value will be repeated 8 times. And here 42 is just what happened to pop up when I did this example. Nothing to do with the hitchhiker and the answer to life. But essentially in this case, only one random element is sampled. So the function is called once and then copied 8 times. And that's an issue that we have found in multiple projects, and it's a pretty devastating issue. If you're trying to generate a random key, this is not a very random key. There's a pretty simple fix, although it is Rust, so the syntax may be a little bit scary. But the way to actually generate a random vector would be to instantiate a range of values, 0 to 8, and then map every one of these values using this map function. So Rust has a number of kind of functional programming type of functions. And so you map every one of these values. You don't actually use the value itself, which is why there's this closure with an underscore that doesn't do anything with the value. But for every one of those 8 values, you do generate a new random value. And then you collect everything in a vector. And so that would be the way to generate a random of 8 elements, 8 random elements. So speaking of maybe more complex operators, this is the topic of the second theme here, which I have called overzealous functional programming constructions, because sometimes when we have access to interesting complex functions, people love to use them, sometimes without really thinking about what actually happens or could happen. And so we often see very complex usages of the zip function, map, that we have just seen, or filter. And this example here, we'll specifically talk about the zip operator. And so zip takes 2 vectors, 2 iterators, for example, A, B, C, and 1, 2, 3, and then it will zip them together. That is, it will create an array of pairs of values that corresponding to elements of the 2 arrays at the same indices. And so if we have, as we said, A, B, C, and 1, 2, 3, if we zip them together, we will get A1, B2, and C3. These operators can be pretty complex. They have some intricacies. And one specific one is zipping unbalanced list will return early. And so if the lists don't have the same size, the operation will essentially only go until the smallest of the 2 lists. And that's a classic example of a signature bypass in specific schemes. So we have found numerous issues with multi-signature schemes where someone could bypass the security by using unbalanced lists. And I'm going to show you exactly how this works. And so for those who might not be aware, a multi-signature scheme would be a scheme where we have multiple participants signing a message. Instead of having just one single public key, a signature for a message, we would have a number of them, and then we would require, so the verifier would require that all of them are correct in order for the message to be considered valid or verified. And so one could go about implementing the verifier function as follows. The function will take a vector of public keys, a vector of signatures, and the message. And then the function will zip public keys and signatures together, as we have seen in the previous example. And then for every one of these pairs, it will check whether the key verifies the signature on the message. In this case, we have a multi-signature scheme with an n out of n verifier. So we want every single one of the signatures to be valid in order for the message to be considered valid. And so how this function is implemented is that as soon as it encounters a signature that doesn't verify, then it returns false. If at the end of the loop, everything is correct, we haven't returned, then we just assume that it's correct, it's true, and then the function returns true. So now what happens if one of the 3 participants is malicious, and instead of sending their public key and a signature, they send an empty public key with garbage, with anything as a signature. Then essentially we would zip 2 lists of different sizes. And so here I've just kind of marked this array of public keys pk1, pk2, and then the third element would actually be nothing. So the list would only be like only contain 2 elements, but I added that null element just for good measure. So if we were to zip a list of size 2 with a list of size 3, then the resulting list would only contain the first 2 pairs. And so if we were to pass that through our function here, we would first consider the first element, the first pair of key and signature, try and verify, it verifies, so we're happy. We proceed to the next iteration. We verify the second element, second pair in the list. It verifies, and then we get to the end of the list. We return true, and then this is essentially a pretty simple signature bypass just by sending unbalanced list to that verification function. The third theme here I want to talk about is release versus debug mode. So when developing Rust code, usually one uses debug mode to write tests and to run and to try and debug their code. But then when deploying code, the implementation would be compiled in a release compilation profile, and this may change the integer overflow behavior. Well, it does change the integer overflow behavior. Specifically, when compiling in debug mode, if we encounter an overflow, this will cause the termination of the program, which is very handy when you're writing tests, when you're just running your code on your machine. But in release configuration, the computed value will wrap around. And so as an example, if we have this value A here, which is just a byte, an unsigned 8-bit integer, we assign it the value 255, and then we add 1. In debug mode, we would have a panic. But in release mode, A would be equal to 0. And so you can imagine how having discrepancies here could lead to issues in real life. Instead, one should use operations that have the same behavior in debug and release mode, such as saturating add, which will saturate at numeric bounds, meaning that A in this case would be equal to 255. The fourth theme here I want to talk about is inconsistencies between languages. And here we're going to look at two operators. The first one is going to be this not operator, which behaves differently between Rust and C, for example. So in Rust, when applying this exclamation mark operator to integers, the behavior is different in C. So in C, you may know that this will enforce Boolean operations. So if we do a not of 0, it's going to be a positive value, which is going to be interpreted as true. But in Rust, the exclamation mark operator performs a binary negation, which is equivalent to this tilde operator in C. This may be additionally hard to find or to catch in Rust because of the macro syntax, which uses lots of exclamation marks. And so a real-world example of where this happened also related to a signature verification bypass, where this ensure macro tried to make sure that the number of signatures was larger than or equal to 2. But they used this exclamation mark operator. So if the list of signatures, so if signatures.len was equal to 0, then we apply the not operator, which is the negation operator, and then this would be the max unsigned integer type in this case, which is larger than 2, and then it would just pass. So in this specific case, providing a list of signatures equal to of length 0 would have succeeded in the verification. Another example here. In this case, this is about right shift, and so Rust has support for both unsigned and signed integer types, and it does so natively. The behavior of the arithmetic right shift is different depending on the type that we're trying to shift. As a comparison, Java does not have a primitive type for unsigned integers, and the values are interpreted in 2's complement. And so when performing a right shift, you actually have two options. You could either do an unsigned right shift or a signed right shift, where the 1 bit or the signed bit is actually maintained. And I'm not going to go into too much details here, but not too long ago, we reviewed a PRNG implementation that was translated from Rust or maybe Go to Java, and so they forgot to change the right shift operator to this like 3 chevron one, which is the unsigned right shift. And this led to a pretty broken PRNG, where here I just plotted the probability of getting any given value. And so this PRNG had over 20% probability of obtaining the value 255, the max byte size. byte value. And so, yeah, this is a pretty broken PRNG that shouldn't be used in practice. I have a fifth category here, but I know I'm kind of running out of time. So here I'm just going to caution you against the use of too complex data structures. And languages like Rust have support for many different types of data structures like maps, trees, and sets. Under the hood, they are implemented using hash maps, index maps, B-tree maps, or B-tree sets for sets, and so on. And all these data structures have slightly different use cases, which is really good because they provide a lot of flexibility, but they also have differences, for example, regarding the order in which elements are accessed in a given map or dictionary, which can also sometimes bite developers. So now that we have looked at a number of bugs, how to actually avoid those bugs, well, the first thing to do is to test. Just write as many tests as possible, try to test those edge cases, and to that extent, you can also try and do static analysis. And here I'm just going to call out two specific tools that are very powerful, although quite different. First one is CodeQL, which is a semantic code analysis engine, where you can kind of query your code. It has pros and cons. It is quite powerful, but unfortunately, you need the code to build. And when we do cryptography reviews, we don't always have the code, the whole project. Sometimes we just get sent files, specific files or specific parts of the implementations, and we're not able to actually run the code. This is where semgrep, which is another static analysis tool, comes into play. And semgrep also allows you to kind of look for specific patterns in your code, and semgrep could be used to try and identify some of the vulnerabilities that I have talked about today. And obviously, more experience and very careful review is also a way to try and avoid bugs. When developing, having a good review process for your code is a must. So in conclusion, I have presented a couple of common vulnerabilities in modern programming languages. I still want to say that you should use programming languages like Rust or Go to write crypto code. This talk is not intended to dissuade you from doing that, but you should do so with care. All inputs should be validated, and as many tests as possible should be written, not only unit tests, but also end-to-end tests, and also fuzz testing is something that we see quite often as well, and that is very valuable for finding some of those very, very specific and difficult to pinpoint bugs. And finally, a bit of a shameless plug here, but hiring an additional pair of eyes is also never a bad idea. And here's my contact information. And with that, I'd like to thank you for your attention, and I'd be happy to take a few questions.
Let's thank our speaker. We have time for maybe one or two. If you want to come up to the microphone, introduce yourself and affiliation if you'd like.
Yeah, my name is Bob Relia, and I'm from Red Hat. Is there any work to look at how to make side channel safe implementations? That's the one thing that we were running into when we wanted to implement crypto in Rust, was we really do know how to make things side channel safe, or at least after our testing we can figure out how to make them side channel safe in C. But with Rust, it wasn't always clear that Rust was going to do something that wasn't safe, and it wasn't really one of the things it was worried about initially. So is there any work on that?
I'm not personally, I'm not affiliated with the Rust Foundation or what they exactly do. I know constant time code is a big issue in Rust. Like you're just kind of at the mercy of your compiler, and sometimes things can change without even you knowing. So I don't think any specific work is being done, or I mean, I'm sure tons of little projects are popping up and are trying to achieve some things related to constant time code. I think we're still pretty far away from it, unfortunately.
Hi, I'm Dave Vulnerable from Booz Allen. I was wondering if you're aware of any AI tools that could be used for testing or bug detection.
I am not, but I'm sure there will be a time where we will be using tools to kind of guide our reviews. But currently, I have not seen anything very promising in terms of that nature.
Thank you.
Yeah.
Thank our speaker one more time. He also has worked on web security since 1992, including working with Tim Berners-Lee. He'll be talking to us today about how will post-quantum crypto systems fail, which I'm sure we'd all like to be able to know.
Thank you very much. So, yeah, I was asked to come and talk about deployment experience, and yeah, in half an hour I don't have enough time to cover that topic. Don't even have time to cover the failure mode. You'll notice that the previous speaker was also talking about failure modes, and there's no overlap really between his talk and mine, and I left a lot of them out. So, what's going to go wrong? Well, big green button. Okay, so one of the fails that I spotted, I was proposing, I'd just taken out all my code from my distribution and replaced it with the NIST stuff. And somebody said, oh no, you don't want to do that. That's reference code. You don't want to use that. You've got to wait for the experts. And, you know, I don't like being called a security expert. I don't know if they exist. I believe in a community of security expertise. And, you know, I know, well, the experts, it takes time for us to become experts, and we mostly learn from the mistakes. Hopefully, if you're lucky, the mistakes of other people. So the experts, they are, if we're lucky, the future us. So don't wait for the experts. Start experimenting now. Mistakes are going to be made. But you know what? That's okay. Because we can choose where to make the mistakes. Do not make your mistakes on whitehouse.gov, or nuclear power plants. Been there, done that. Choose something like doorbells. Choose something where post-quantum is way overblown for the security requirements, and let's learn from those. Second thing is, well, you might be saying, well, we can wait. There's no hurry. I mean, like, you know, these post-quantum systems, you know, super fridges haven't been moving very fast at all, you know, 1 qubit every so often, and, you know, they have to spend twice as much to build the fridge. And, yeah, well, I have a slightly different perspective on this, because when I did my computer science degree, I walked into the nuclear physics building. Yeah, it wasn't my fault, you know, they're next door, you know, easy mistake to make. And one of the things that I learned from the nuclear physicists is how to recognize a physics experiment. And, you know, at the moment, quantum computers, you know, I've used them, you know, they're physics experiments. And here's the problem. The other thing I learned about from the physicists is that they're really, really good at getting funding. They're much better than we are. I mean, like, look at the whole PQC system. That's our research budget, and they're spending it on physics. And here's the problem. Over the past 6 months, about 100 million, 200 million has gone into venture capital funded quantum computer startups, and they're all doing trapped ion. And whereas super fridges were never going to deliver scalable quantum computing, trapped ion could. And we might be finding out that we might be in a post-quantum world sooner than we expected. We can't delay. But even worse, you don't even need that quantum computer to do a quantum attack. When we were, doing the web, and I was at the Web Consortium, and one day I get this phone call from Jack Fox. Whitehouse.gov is down. Do you know anybody in the Washington, D.C. area who can lend us an internet router? And this was 1995. This was in the days where you couldn't just go into Fry's and buy one off the shelf. In the 6 hours it took them to get Whitehouse.gov up, a bunch of Serbian hacktivists, and we were bombing Serbia at the time. They hacked a bunch of federal sites, defaced them, and then called up Wired magazine. And so I had a reporter from Wired asking me, these Serbian, they've taken out whitehouse.gov. And I was having to explain, no, they haven't. The router's gone down. So, and the point here is reputation attack. Reputation attack is probably going to be the first post-quantum attack we see. And think about it, our most vulnerable infrastructure is the financial infrastructure, and finance runs on reputation and trust. So this is serious. Okay, so my deployment perspective comes from building this pile of steaming technology, as people put it, called the mathematical mesh. What am I trying to do? Well, I did public key infrastructure for 20 years. About a decade ago, I started to ask, why aren't people using it on the client? And I started to think, well, maybe it's because we didn't manage the private key. So I've been doing private key infrastructure, and so the loose idea is bind all of Alice's devices together into some sort of digital gestalt, and then the mesh is going to squirt in the private keys and all the credentials it needs to do activities. And of course, where does this come? And I'm using threshold cryptography for this. Can't do this in PQC so often right now. But some of the applications that I'm trying to provision with those credentials, they want to be post-quantum. So I've had to look back and think, how do I make this key management system post-quantum as well? And so things that I've come up with along the way that are the roadblocks. One of them, let's just take a step back and look, what do we mean by going post-quantum? The dip your toe in the water version is, well, we're not going to do a fully post-quantum system yet, but we're going to make it so that you can upgrade to the post-quantum stuff later on. Second stage is, well, we're not going to do post-quantum everything, but we're going to make sure that the stored data that we have is going to be secure against post-quantum attack, the store and decrypt. And then finally, you've got to the full PQC. And, at this stage of the game, I'm not sure that anybody has the experience to go full PQC. Challenges that I've hit along the road, well, the public key sizes and the signature sizes really do bust up my protocols. And even worse, there's no threshold modes. The one thing that isn't a challenge is the size of the private key, because you don't ever need to store the private key. All you need to do is to store the seed and have a deterministic method of going from the seed to the private key. I'll come back to that in a moment. But again, there's no way of doing threshold generation for PQC. And that really hurts. And so the third fail is getting too creative. So you've got this running system that works fine. And you just got to squeeze in that PQC, and it's taking a few too many bits. And this is hitting me hard with my profiles. Mesh profiles using elliptic curve, they're only a kilobyte. As soon as I start putting in ML-Chem and ML-DSA, they go up to 10. And when I start to look at my message sizes, Those exploded from 1,200 bytes, enough to get it into an Ethernet packet, and now they're 50 kilobytes. And, that requires us to start to think and get creative. And getting creative is not what you want to do. So one of those things that I've been working on is deferred public key. You have a signature. You don't necessarily need to put the public key in the cert. You can put the digest of the public key in the cert, and then put the actual public key in the signature. And that means that instead of having 8 kilobytes of overhead for adding your MLDSA keys, you're adding 64 bytes, which isn't that much. Of course, you can't play this trick from encryption, because the thing about encryption is the other person needs to know the public key before they can encrypt. And so this gets us to the idea of multiple certificates. I'm doing this in my own stuff, which is, it's not a standard you've heard of. We could add this to PKICs. Instead of adding the additional algorithms as subject public key info, we'd add them as extensions. But the idea here is you have a certificate that instead of just giving one public key for the subject, gives a list of digests of public keys, and then you have a fat signature on that certificate that has all the signatures for all the key types, and then some mechanism for going from that fat certificate to a thin certificate that just has a root of trust, an accreditation for one particular algorithm. And so that's a trick that you might be able to play and might get you around some of those data size limits. And yes, this is kind of like, there are many ways that this can go wrong. And this is the sort of thing where people get I think that I can get this to work and get it secure. But if you layer too many layers of creativity on top of each other, people are going to get hurt. And in particular, you want to have large numbers of eyes from outside your development community if you're going to go down that path. The security world, stay with the herd. It's safest. Fourth fail is upgradable that isn't. And this is something that I've been seeing a lot of people saying, oh, this is great. We're not going to do the PQC now, but you know what? We've got a PQC root in our firmware, and we can take a software update that will take us into the post-quantum world. And yeah, that could have worked. For the past 20 or 30 years, we've been screaming about the IoT vendors saying, 8-bit CPUs and 32 kilobytes of RAM, that's not enough to do decent crypto. Can't do RSA, just give us a bit, give us a bigger CPU. And so finally, the world was starting to move to Raspberry Pi type systems, 32-bit CPUs, half a gigabyte of RAM. All those constraints went away. Well, no, what happened is that they've now generated this nano class, nano Raspberry Pi and ESP32. They have a nice fat 32-bit CPU that can do all the nice ECC crypto that you want. You can even do RSA if you want. It's got 1/4 of a megabyte of RAM, and that's enough to do PKICs and TLS. But if you want to do a hardware security module in them, fine. But if you want to run an application and also upgrade to ML whatever, you're probably going to find that although you can upgrade the device to this new threshold crypto, there's not going to be the memory to run it. I think that we're going to be seeing a lot of failures of that type where it was supposed to upgrade but didn't. Fail number 5 is the opposite, which is the downgrade attacks. And this is something that really worries me as a protocol designer, where you design something with perfectly good crypto, and the attacker works out how to run the rubbish crypto instead. And the thing that I'm currently trying to work out whether I've got a problem or not has to do with mock messaging. So there's this protocol in ITF called Media over Quick. It's a really great advance over WebRTC. Instead of having the web and Chrome and, a metric gigabyte of code surface area with your voice and video communications, all you have is the codec and Quick and your crypto, and that's it. So, we can reduce our surface area. All it lacks to turn that into an open service version of Zoom or Signal where you can choose your service provider is a method of exchanging contacts. Well, I've got that already. And a presence protocol. So I was writing a presence protocol, and I probably would have finished it, only I got the invite to speak here. So I've been doing post-quantum instead. And the particular problem that really worries me here is that at the end of my presence protocol, the output from that is, here's an IP address, here's a port, and here's a shared secret. And with those, you hand those over to mock, and it's sections per session. And here's the problem. As a protocol designer, I want to know, is that session that it sets up going to be post-quantum secure? And the problem here is that mock is also end-to-end secure. And how do I avoid it doing that thing that those firewalls did the other day? You remember the firewalls that they were doing RSA 2048-bit key exchange? And then they did an ephemeral with 512-bit Diffie-Hellman. And somebody broke the Diffie-Hellman key and chaos ensued. Same sort of attacks worries me, where you set up a perfectly secure post-quantum end-to-end thing, and then the thing that you hand over that nice post-quantum safe shared secret to then goes and fiddles with it in the name of forward secrecy. And the thing, there's two problems here. One problem is there really a problem? And secondly is, can I prove to myself that there isn't a problem? Probably there shouldn't be a problem, but it's probably going to take me several weeks of code spelunking and spec spelunking before I've convinced myself that it is. And so one of the things I'd like to propose is that we don't throw shared context away. Because traditionally, the thing that allowed those firewalls to be broken was that they did a key exchange. Alice and Bob had their credentials, they established a shared secret, and then they generated a bunch of ephemerals and used just the ephemeral to generate the shared secret that they used on the session. And all you need to do to close this hole is do 1 and 3 as before, but make sure you ratchet in your original shared secret into the session key, KDF. And if you've got that in the protocol in a way that is really visible, then I can audit your protocol in a few hours instead of having to spend a month code spelunking. Okay, another way that I see dragons coming are side channels and kleptography. Now, the good news on the kleptography front is, when I started writing this talk, I was looking at those ML-Chem and ML-DSA private keys, all those huge matrices And I'm thinking, oh, yum, 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 I can really play some cryptography games here. Oh, side channels is where you accidentally leak the private key or whatever. Cryptography is when you design the system to deliberately leak it. So you have an RSA HSM that advertises its private key to somebody who knows the back door. And you know, those matrices in MLChem and MLDSA were looking really like red flags for kleptography. Well, I think that the community's come to an agreement on that we're going to shut that door and that we're going to use the seeds, the private key seeds that are used to generate those matrices as the private key storage and not store the matrix itself. And that shuts the door to kleptography in MLDSA. MLChem's a bit different in that there are two seeds, one to generate the private key, the other to generate the noise. I don't like them being two. I would like them to be a digest between anything that comes to me from the outside and my keys. So I think that we'll win that one. Side channels. Don't just think about timing attacks. Think about power. Think about differential power analysis. You know, it was 18 years after RSA was designed before we got differential power analysis. So don't imagine that we're going to know what the side channel vulnerabilities of MLChem or MLDSA are immediately. It's going to take time, and there may be an attack that we didn't expect. And final fail is bright, shiny objects, because at the moment, we just spent the past 10 years fixated with blockchain fixing all our cryptographic problems. And 10 years later, has it solved any of them? I mean, we're not even using blockchain for the thing that it could do, which would be notarizing digital evidence. That's how much we failed there. I think that there's a risk that we do the same thing with PQC. And the thing is that if we look at the actual breaches, transport security, it's been a solved problem for about 20 years now. We've been incrementally improving TLS. But if you look at where the breaches are, for every one of the past 20 years, the top 19 of the top 20 breaches have been breaches of data at rest. And if you're going to secure data at rest, you're really going to want to use separation of roles as part of your solution. And right now, post-quantum can't do threshold. And it's going to be at least 5-10 years before we even have a candidate that can do that in a standards approach. So we're going to need to have hybrid systems for our data at rest security solutions. Use separation of roles. So the question then is, what happens if somebody builds a post-quantum computer? You can set it up so that if somebody's got a quantum attack, yes, if they compromise the key server and they also, if they compromise the key server, then it's going to be game over. But, maybe we can use HSMs to make that an improbable attack. But you can design it so that only the separation of roles thing falls if the CRQC is built. Okay, so in conclusions, start now. Don't wait for all the pieces to be in place before you start getting experience of building post-quantum systems, because we won't know how to build them until we build up the base of experience. Learn from other people's errors if you can, but don't be afraid to make them yourself. Reputation attack might well be your biggest vulnerability, and we're absolutely going to need hybrid. at least until threshold is out there, there's no substitute that I can see. So that's it. Got my site there, my contact details. Got time for a couple of questions, I guess. Thank you very much.
Thank you, speaker. Once again, please come up to the microphone, name and affiliation if you'd like to identify yourself.
Oh, and I will be doing a podcast going into further issues in more depth in this, because there's an inexhaustible amount of material.
Manoj Kumar from IBM. Could you say a few more sentences on why keeping a seed that generates your keys is more safer than keeping the entire matrix?
Okay, so you have a deterministic process from getting from the seed to the matrix. And so if you've got the seed is telling you, this has been generated in a particular fashion, and you know that there's a limited amount of variability that the generator of that key has had as they did it. So you've got a hardware security module, and so the idea is that it's from a vendor that you trusted, but you shouldn't have. And they've designed it in such a way that it is going to leak the key, the ultimate random seed that it has inside it, to the outside. And so if you have it locked down so that it's generating from a seed, there's much less ability to do that than if you give them that matrix, because if they've got the whole matrix, well, then they can play games like, okay, I'm going to make the noise in this area a little flat, so that as the thing is used, it's going to leak a bit of information to somebody who's on the other side who knows, well, this value is always a 1, this value is always a 3, or whatever. And you can leak information that way if you've got that whole matrix. If, on the other hand, you've got a seed and then you've got to go through that SHA-3 shake stuff to generate that matrix, you've got a lot less rope to play with. Doesn't completely eliminate the attack, but it makes it a lot smaller window.
So, per signing, for example, in signature algorithms, per signing, you will regenerate the key every time.
You'd regenerate the key each time you started up that particular key. You wouldn't necessarily need to keep it in memory the whole time.
Fair enough.
Which is another reason that folk wanted to go to the seeds, because then they can have an HSM that instead of having to store that big matrix, it could just store the seed, and it would have a lot less memory requirement.
Says that generating the matrix in the CPU is more secure than leaving it in the HSM, because that can be leaky.
Yeah.
Okay, now I got it.
From the kleptography point of view. From side channel, on the other hand, well, you've just generated yourself a whole new problem to make side channel safe. So, yeah, there's no free lunches.
All right, let's thank our speakers.
Thank you very much.